Welcome to our discussion for Chapter 11. Today we're going to talk about magnetic fields. We'll talk about how they're created. We'll talk about how we can calculate their direction, how we can calculate their magnitude. We'll talk about permanent magnets, what causes what causes a piece of material to become permanently magnetized, and we'll also talk a little bit about devices called solenoids. So magnetic fields, we got a lot of ground to cover. I'm going to move pretty quickly through it, but I think that a lot of today's images are going to be helpful for understanding what we're talking about. The unit of magnetic flux density is the Tesla, named of course after Nikola Tesla. You probably have heard of him. He's very popular in culture today. He's best known for his contributions to alternating current. He's also known for having quite a feud with Thomas Edison, who was a big advocate of DC, direct current. And the fact that we use AC today primarily gives you an idea of the fact that Tesla won that fight. His understanding of electricity and magnetism was so great and so ahead of his time that people actually believed that he was supernatural. They felt that he was too smart for a normal person, that he must have some sort of magical abilities. He wasn't supernatural, but he was very smart. And he was also very dedicated to his field. He would often give away his inventions without patenting them, just so that other scientists could and engineers could improve them and make them even stronger. He spent all of his money working on his inventions and working on his theories, and he died penniless in 1943. His work wasn't really well recognized until the SI unit for flux density was named after him in 1960. Okay, time for one more mathematical prelude. This is the curl. Hopefully this will be the last major mathematical prelude we're going to see. Remember that we've already talked about the divergence, which is whether or not there's a source or sink of a vector field at a particular point. We've seen the gradient, which is the vector derivative of the function. And then the third is the curl. And the curl is really talking about how much is a vector field rotating. So is it rotating? Is it revolving? Think of like if you have water flowing in a river, that is not rotating, but water in a whirlpool is rotating. Think about wind blowing in a straight line, no rotation, but a hurricane or a tornado definitely has rotation. And we're going to see the same thing when we talk about magnetic fields. We can represent the curl of A as del cross A. You'll remember that we've seen that del operator both with the divergence and the gradient. We're going to use it again here. And the curl of A, it can also be represented by equation 11.2. Equation 11.2 is a little bit complicated and very dense, so I just wanted to take a minute and unpack that. I've also drawn figure 11.1 here to help to illustrate what's going on with this equation. You'll notice that equation 11.2 includes this closed line integral, and so I've shown the line integral here as a dotted red line. In figure 11.1, that dotted red line is just a circle, and you can imagine then that if this vector is in fact rotating, then it will tend to line up in the same direction as this line vector, as this line integral. So we're going to find that a measure of rotation is whether or not the line integral is non-zero. But of course, the size of the line integral will help to determine how much of that vector there is. So we're going to divide by the surface area. So that surface area is this delta S that's inside of that circle. And I've shown in figures A, B, and C that the vector does in fact have rotation. So it is in fact at all points, it is pretty much generally pointing in the same direction as the path. The black arrows there represent the vector field itself. But I'm shrinking the size down as I go from A to B to C. I'm shrinking that size, which is this limit as delta S goes to 0. So if we take the limit and shrink that down to the point where, as shown in point C, in part C, it's almost a point. And we would shrink it down even further so that it literally was just at a point. And we'd be able to see how is the rotation just around that single point. And it turns out that if you take del cross A, you'll be able to figure that out. So just wanted to give you also a couple of figures here that would show vector fields that have rotation and those that don't have rotation. Obviously, part A here, figure A, does have rotation. And you can see that if I were to take a line integral around that dotted red line, that in general, the vector points tend to be in the same direction as the path. And so we're going to tend to find that they're going to add up. But in part B, you'll notice that, well, maybe here it tends to be sort of pointing in the same direction as the path, but down here it's actually pointing in the opposite direction of the path. And those two are going to cancel each other out. Here it's maybe partially in the same direction as the path, but over here it's in the opposite direction of the path. And similarly here it's partially in that direction, but here it's partially in the opposite direction. Those will cancel each other out. And in this area, it tends to actually be perpendicular to the path. So that it turns out that in figure B, this vector field has zero curl, because all of the components of that line integral are going to cancel each other out. And in part C, it's pretty obvious that the vector field does not have rotation, and that's because the vector field in black is perpendicular to the circular path in red at all points along the path. So in part B, we had to say, well, there it's going to cancel it out. But in part C, I can say, no, pretty much every single component of that integral is going to be zero. Never is there anything that has to cancel out, because they're always all zero. You might say, well, how can I calculate the curl? I understand now what it does, but how do I calculate it? And the answer is using the determinant method for doing the cross product. You'll remember that way back in chapter 1, when we were talking about vectors for the first time, we introduced this concept of calculating a cross product. And so we're going to calculate the cross product of the del operator with the A vector. And so you can see here that the cross product is a determinant. We have a number of ways of calculating this determinant, but I'm going to show you, I'm going to remind you of what I think is the best method, which is the diagonal method. If you look way back in figure 1.5, you can see that diagonal method. We're also going to see it in a couple of examples here coming up. Equation 11.3 can be rewritten as equation 11.4. It's just that we've now expanded out the determinant and made it so that it's individual partial derivatives. But please don't memorize equation 11.4. Memorize equation 11.3 or have it readily accessible to you, but don't memorize equation 11.4. It is a waste of your time, and you're extremely likely to make a little mistake. If you get one negative sign wrong, then you've sort of ruined the problem. So equation 11.3, that's the one to focus on. Just incidentally, we can also have versions of this for in cylindrical coordinates and in spherical coordinates. I just wanted to really emphasize the importance of this prefactor right here. Both in cylindrical coordinates and in spherical coordinates, there's a prefactor that is outside of the determinant. You're going to be tempted to pull that inside the determinant and say, well, you know, I've got a row right here. Couldn't I just cancel that row with that 1 over row? And the answer is definitely not, because you're going to need to be taking derivatives of these functions, and sometimes the derivative involves the row, but the 1 over row is always going to be outside of the derivatives. So my advice to you is it's not really advice, it is a fact. Don't try to pull those into the determinant, but don't forget them either. One of the most common mistakes in solving these equations is to forget those prefactors. Okay, let's do a couple of quick examples here. I've got a vector field here that is 3 different components in rectangular coordinates. So right away I can tell you that we're going to use rectangular coordinates. We want to calculate the curl of this vector field f. So the curl, remember that the del operator is a vector, so I'll put a little arrow over it. The curl of f is equal to, and I'm going to have a determinant here, and that determinant has the unit vectors on the top row. In the middle row, it has the 3 partial derivatives. And on the bottom row, it has the 3 components. This component right here, we've called a sub x. This component we've called a sub y. And this component with the negative sign, we've called a sub z. So I'll have 3x, and I'll have 5xy, and then I'll have negative 8xyz. And we close the determinant. And really our only job then is to figure out this determinant. Now, the way that I would recommend that you figure out the determinant is the method of diagonals. And here is the full version of the method of diagonals. You repeat the first column, and then you repeat the second column, and then you're going to draw diagonals going down and to the right, and diagonals going down and to the left. That's the method of diagonals. You might say, well, what good does that do us? What we're going to do is we're going to take every element that's on each of those right-leaning diagonals, and we're going to make those be positive. So I'm going to take a sub x times the partial with respect to y of negative 8xyz. That's positive because I'll write a little 1 right here. Oh, hold on a second. I'll write a little 1 right here to emphasize. Oh, I'll just write a little positive. So a little positive and a little positive, and then these are going to be negative because they're the ones that are leaning to the left. I don't know if it's fair to say which one is leaning to the left and leaning to the right, but it is northwest, southeast, and then northeast, southwest. So I've got 3 terms that are going to be positive, and they are the ones that I labeled with plus signs there. Partial with respect to z of 3x. So that's the second of those. Yep, just double checking that. Plus a sub z partial with respect to, wait for it, x, and then 5xy. Yep. And then we've got to do the 3 that are negative. So minus a sub z partial with respect to y of 3x minus a sub x times, whoops, don't want that quite yet, times the partial with respect to z of 5xy minus a sub y partial with respect to x of negative 8xyz. Now some of these are going to be pretty obviously 0. What is the derivative, the second term, what is the derivative of 3x with respect to z? Is just 0. There is no z dependence. Let's see, the partial with respect to y of 3x, that's equal to 0. What is the partial with respect to z of 5xy? That's equal to 0. These other derivatives are going to be fairly easy to calculate. We have a sub x times the derivative of, with respect to y, of negative 8xyz. Well, the x and the y are going to be considered constants because it's a partial derivative. So we get negative 8xz. Plus, we have a sub z, and the partial with respect to x of 5xy is just 5y. And then we have minus, don't forget that minus sign. Oh, it's a minus of a minus actually, so it becomes a plus. Plus a sub y times the partial with respect to x of 8xyz becomes 8yz. Let me just quickly double check that I got all of those the same. Very good. So that's my final answer. And of course, you could plug in the values of x, y, and z for a particular point, and at that point, you could determine whether or not there's rotation at that point. I didn't decide to do that because we got a lot of ground to cover today, but I did decide that it was worth the time for you to see an example in cylindrical coordinates. So let's consider, we have a vector here, and oh, I don't know what that was all about. So I have a vector here, and it's going to be, if I'm at a certain distance rho away from the center, then I've got the a sub phi is pointing in this direction. So and the strength of that is going to depend upon the rho. You can see that as rho increases, the rho is negative in the exponent here, so that the current density, I'm sorry, it's not a current density, it's just a vector field, is going to decrease. So what is the curl of B? We know that this is going to be equal to the del cross B, and from equation 11.5 up above, this is equal to 1 over rho times a determinant, and that determinant is going to have the unit vectors on the top row, so that's going to be a sub rho, and then there's going to be rho a sub phi, and then there's going to be a sub z. And then on the second row is going to be the partial derivatives. So there's the partial with respect to rho, and then there is the partial with respect to phi, and then there is the partial with respect to z. And then the bottom row contains the actual components of the vector. In this case, there's only a phi component of the vector. So the rho and the z columns get 0. And if you look back up at equation 11.5, you can see that there is a rho right here. So we need to be sure to account for that rho. And so I'm going to come back down here, and when I'm writing this determinant, I have to write rho times the phi component, which is 10 e to the minus rho over 2. Now all that remains is to actually do the determinant. I'll use the method of diagonals. I can do, this is going to be a term that's positive, but it's the partial derivative of 0 with respect to phi, so that's just 0. Then I'm going to have a partial derivative with respect to z of 0, so that's also 0. Then I'm going to have a sub z times the partial with respect to rho of rho 10 e to the minus rho over 2. So there we have partial with respect to rho of rho 10 e to the minus rho over 2, and that's in the a sub z direction. And then we have three negative terms, but this one, of course, is 0, so that's minus 0. And then this one is the partial of z, partial with respect to z of a thing that doesn't have any z dependence, so that's 0. And then we have the partial with respect to rho of 0, and so that's 0. So 5 of the 6 terms have gone to 0. That's very convenient for us. What we're going to need to do, though, is we're going to have to do the one term that isn't 0. I'm going to pull the 10 and the a sub z out in front, and then what's left is just rho e to the minus rho over 2. And so that's a product rule. It's not too bad. We have, I'll take the derivative of the first factor, so that's 1 times e to the minus rho over 2 plus, and then I keep the first product, I keep the first factor, and I differentiate the second factor. And when I differentiate e to the minus rho over 2, I simply get a minus 1/2 times e to the minus rho over 2. And I can then multiply all of this together, and when I do the arithmetic, I end up with, oh, darn it, I forgot the 1 over rho. So there is a 1 over rho. That was, I talked about how you don't want to forget that. 1 over rho, this is 1 over rho times all of this. So this is equal to, and then I'll just put this in the most compact form that I can, 5 times 2 minus rho e to the minus rho over 2, all of that divided by rho, and that's in the a sub z direction. Now let's talk a little bit about magnetic fields, because today we're really going to open up a completely new part of our discussion of electromagnetic field theory. Until now, we've seen that static charges, charges that don't move, create electric fields. And even charges that do move will still create electric fields. But charges that do move also create magnetic fields. So the same charge will be creating both electric fields and magnetic fields as long as it's moving at a constant velocity. And I've shown here in figure 11.3, this is showing that if you have a current I, that it's going to be creating a magnetic flux density around it at all points. So anytime that you have a piece of wire that you've run a current through, you're going to be creating magnetic flux density around that wire. Every single wire you've ever used in an ECE lab has had magnetic flux flowing around it. And that usually it's not significant enough to affect the results, but on occasion, and especially at higher frequencies, it definitely can. Now this little thumb here over to the right is showing that if you put your thumb in the direction of the current, then your other 4 fingers will wrap in the direction that the magnetic flux density will flow. So in this picture, it means that behind the current, it's going up. At the top, it's coming toward you. In front of the current, it's going down, and at the bottom, it's going into the page. That's really hard to represent, but yeah, it's hard to represent that in a two-dimensional picture. But just put your thumb in the direction of the current, and then your fingers will wrap in the direction that the magnetic flux density is going to flow. You'll notice that we represent that magnetic flux density by the letter B. So just as we have standard E for the electric field, we had D for the electric flux density. Now we have a third variable, B, which is representing the magnetic flux density. The units of magnetic flux density are Tesla, as I mentioned to you earlier. That's equivalent to a kilogram per amp second squared. Using the other fundamental units. Sometimes you'll run into somebody who's very old school and they'll refer to it as a Weber per square meter. Not very often. It was called the Tesla way back in 1960, but sometimes you'll see that, and I just want you to be prepared for it. Weber per square meter is exactly the same thing as a Tesla. A Tesla is a very large unit of magnetic flux density. Think about the fact that an amp is a pretty large amount of current because a coulomb is a pretty large amount of charge. So if you get a magnet that's delivering 1 Tesla, that is a very powerful magnet. You know, for comparison, the electromagnets that they used to pick up cars at the junkyard is about 1 Tesla. And it can pick up a car that weighs like 2,000 pounds. So that's a very powerful magnetic field. Sometimes we're going to use a unit called Gauss, which is equal to 10 to the negative fourth Tesla. So just if you run into a Gauss, just know that it's 10 to the minus fourth Tesla. And for comparison, the Earth's magnetic field is about a half of a Gauss. So compared to a Tesla, the Earth's magnetic field is not very strong, but it is strong enough for us to be able to talk about compass needles turning and being able to recognize it using magnetic sensors and so forth. So recognizing a half a Gauss magnetic field is no problem. We can definitely detect that. The most important thing that I want you to take away about magnetic fields today is that they do not have sources and they do not have sinks. In other words, magnetic fields don't ever have a beginning and an ending. They always loop back to where they started from. Every single time, and I'll scroll back up here to this picture, every single time that we see a magnetic field, it's always going to be a loop. And it doesn't have to be a circular loop, but it will loop back to where it started from. It absolutely must. Now, there are some advanced physicists who are trying to study if there's a way to have a source or a sink of a magnetic field. I don't know if they're going to succeed, but they haven't yet. And so what we know so far is that we don't believe there are sources and sinks of magnetic fields. Another way of saying this is that there is no such thing as a magnetic monopole. That anytime you have a magnet, it's always going to come with a pair of poles, north and south. And we'll talk more about north and south of a magnet here pretty soon. But for now, just know that if you say no magnetic monopole, that means that you can't have a point where magnetic fields are flowing away from it, because the magnetic fields must always come back and loop together. In fact, we can represent this by saying that if you have a closed surface integral, so let me indicate, let's draw a sphere. So this is a sphere, and I know it looks like a circle, but it's three-dimensional, so it's a sphere. And if you have a magnetic field that is flowing out, so if there is a magnetic field that is flowing out, then 100% of the time, that magnetic field must wrap around and it must go back to where it started from. And so what we find is that the surface integral will always have a magnetic field flowing in and the exact same magnetic field flowing out. It could be that we would have another loop over here, and maybe this one is flowing this direction, but wherever it's flowing in, it must always flow out. So we can say that the surface integral of the magnetic flux density will always be zero for any closed surface. And we could also say that another way of representing this is that the divergence of B, remember the divergence of B is sources and sinks, it is always equal to zero. Now these two equations are so important that they're actually the second of Maxwell's equations. So it's sort of like when you play a video game and they say, oh, you have to find these 4 magic rings. Well, we have these 4 equations. We've now seen 2 of them. We saw Gauss's law, and in particular we had an expanded version of Gauss's law that allowed for dielectric materials. That was the first equation of Maxwell's equations. And the second one says that there are no magnetic monopoles. That magnetic fields, magnetic flux density never has a source or a sink. It always wraps around back to where it started from. Now, when I took this class, I took it as a junior, and so I was about 20 years old, and at the time I was taught only moving charges will create a magnetic field. And I was kind of shy, and I didn't want to ask my professor a very important question I had, and that question was, what about permanent magnets? The best example of magnetism that I've ever seen in my entire life is a permanent magnet, and it is not explained by what you just said. And it took me 10 years to figure that out. I was 30 years old before I figured it out. And so now I want to explain to you so that you'll maybe only take, a minute and a half to have that same level of stress that I had for 10 years. So there's a little bit of a story that has to come here. So I'm going to take a few pages to tell this story. Here we have a simplified model of an atom. It is a simplified model. This is not the way that atomic physics really works, but we can picture it as the nucleus composed of neutrons and protons, and then surrounding that and moving in circular rotation is the electrons that are sort of surrounding and rotating or sort of revolving around the nucleus. Again, that's not the way it really is, but it is a sufficiently detailed description for the purposes of our story today. So we have these electrons. These electrons are charged particles, and they're moving. And that means that they are moving charges. And moving charges always create magnetic fields. So every atom actually has a magnetic field. Now it just turns out that most of the time those atoms are oriented randomly. And if those atoms are oriented randomly, then each of the magnetic fields, which I'm showing here with red arrows now, so the electrons are circulating around, and if you use the right-hand grip rule, you'll see that actually the motion of the charges is actually creating a magnetic flux density that points up through the center of the atom. But if those atoms are oriented randomly, then they're all going to cancel each other out. You've got an uncountable number of atoms, just this 10 to the 20th atoms, and they're all randomly oriented. There's no net magnetic field. Except if you happen to have a material that's known as a ferromagnetic material, which is iron, nickel, and cobalt, or alloys that contain iron, nickel, or cobalt, then those atoms will combine together into what are called domains. Those domains are maybe about 1 millimeter in size, and within the domain, each one of those domains, all of the atoms line up in the same direction. Some of the domains are a little bit bigger, some of the domains are a little bit smaller, but in a ferromagnetic material, you get these domains. You might say, why? And to be honest, it's a little bit too complicated to describe here. It's a combination of chemistry, thermodynamics, quantum mechanics. There's lots of things that contribute to why these three particular types of materials end up with these domains. So I guess there's still another mystery, but that's the way science is. It's always mysteries all the way down. So no matter how much you understand, there's always something that you don't understand. But we're going to say that we have these domains, but the domains themselves are now randomly oriented. So it's not that the atoms themselves, the atoms are oriented in the same direction within each domain, but the domains themselves are randomly oriented. But if we apply an external magnetic field, as I've shown here, some of those arrows will begin to rotate in the direction of the external magnetic field. And I'm sort of simplifying this here by showing the arrows rotating. In reality, it might be that a domain that was pointed in the correct direction might grow a little bit, and a domain that was pointed in the wrong direction might shrink a little bit. But you can think of it as the arrows rotating. And I know that you'd have to kind of flip back and forth between figure 11.6 and figure 11.7. I've basically tried to show that the arrows tended to move sort of in the direction to rotate to line up with the external magnetic fields. If you apply an even stronger external magnetic field, now essentially all of the domains are going to line up to face in that same direction. And that's reasonable. We want the flux lines to agree with each other. We want the flux lines to line up with each other. We would expect then that these magnetic domains would tend to line up in the direction of the external magnetic field. But the most interesting part of the story is that when we remove that external magnetic field, those those magnetic domains tend to stay pointed in that same direction. Now they relax a little bit, and I've tried to show that here, but that relaxation isn't complete because these materials exhibit what's called hysteresis. Hysteresis is where once a material has been subjected to a magnetic flux density, it will tend to maintain a memory of that effect. So if you remove the magnetic field, magnetic flux density from outside, it doesn't just revert back to the way that it was. It sort of stays permanently in that orientation. Sort of like your college experience. You will eventually leave college, but it will cause permanent changes in you, and it's really impossible for you to eliminate those changes. The same thing is true for these magnetic domains. And interestingly, this hysteresis is how hard drives work. If you wanted to know how does a magnetic hard drive work, you simply take a little electromagnet, a little coil of wire, and you apply a very strong magnetic field to a very tiny piece of the material, and it will permanently change that material to either be pointing north or to be pointing south. And it will stay that way until the next time that it's overwritten. So this hysteresis effect is the only reason that we have magnetic hard drives, which is really very important for modern computer technology. So this is very important to understand. We'll actually also talk a lot about ferromagnetic materials. They're critical in many areas, and you're probably going to get tired of me saying iron, nickel, and cobalt, because if it weren't for those three materials, we wouldn't have electrical and computer engineering. We might not even have modern society. So I just wanted to mention also that if permanent magnets can be destroyed, you can demagnetize them, not just by shattering them, but if you heat them to a high temperature. So if you bring them up to a high temperature, then you've introduced a lot of extra energy into the system, and then the domains can sort of rotate randomly, and they tend to move out of alignment with each other. And also that's a great way to cause a permanent magnet. Is not only do you apply a strong magnetic field, but if you heat the material, then you allow it to more freely rotate to line up with the permanent magnet, with the externally applied magnetic field. So heat can be a very good way to both create magnets and to destroy magnets. Also, if you hit the magnet while it's subjected to very high temperatures, you can also demagnetize or magnetize the material as well. So heating it and whacking it are two ways to cause the domains to rotate, which can either magnetize or demagnetize the materials. Incidentally, compasses are nothing more than a permanent magnet with a very low friction bearing that allows them to rotate in response to externally applied magnetic fields. We'll see this in class, but just be aware that the Earth's magnetic field will cause this compass to line up in the same direction. And incidentally, the Earth's magnetic field is actually caused by the rotation of the liquid inside the Earth's core. So just as we saw that the rotation of an electron around an atom creates individual very tiny magnetic fields, in the same way, the rotation of the molten core, which has a lot of charge in it, is also going to create a very large magnetic field. Now, half a Tesla, you might say, well, that's not such a large magnetic field, but it's across the entire Earth. It's across the entire globe. And that is actually a very significant magnetic field. So we can respond to that. We can use it to our advantage. We use it to our advantage every day as it blocks ionic radiation coming in from the outside world and from the outside of the Earth. So it protects us by having that magnetic field here. If it weren't for the Earth's magnetic field, it would be difficult for life to exist on the planet. And I'm going to scroll back up here one more time. I just incidentally mentioned that the lines of flux density are flowing out of the Earth's North Pole and they're flowing into the Earth's South Pole. And that's actually how a magnet came to have what's referred to as a North Pole and a South Pole. You might think of the North Pole as the exit and the South Pole as the entrance. This is the place. The North Pole has the flux lines leaving, and the South Pole has the flux lines entering. And whether that's a bar magnet as shown on the left or a horseshoe magnet as shown on the right, the flux lines are going to flow out of the North Pole and into the South Pole at all points. It turns out that if you have a whole bunch of these permanent magnets, they will always line up so as to point the flux lines in the same direction. And as those flux lines are lining up in the same direction, that typically would mean, for example, that if you had a bar magnet, they would line up north-south, 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 because you want to always have the lines flowing out of one and into the next. And this idea of magnets, whether they be permanent magnets or electromagnets, lining up to orient in the same direction, that's actually how DC motors work. That's actually how all motors work. We'll talk more about that in a later lesson, but just be aware that if this didn't work, then motors also wouldn't work as well. Okay, so we've seen how magnetic flux is generated. It's generated by moving charges. In particular, we understand how permanent magnets work. We understand how to calculate the direction of magnetic flux lines using the right-hand grip rule. And we also understand that magnetic flux lines are always continuous with never a source or a sink. But how strong is the magnetic flux? How can we calculate the value of B? We know the direction of B, but what is the amplitude of B? And the answer is in what we call Amperes Law. Amperes Law is very much like Gauss's law. What we're going to find is that in magnetic fields, there are a lot of things that are very similar to electric fields. And the thing that is similar between Amperes' law and Gauss's law is that both of them involve a closed loop or a closed path integral and determining how much charge or current is enclosed within that closed loop integral. So in Amperes' law, this is the integral form of Amperes' law. You can see that we're going to need to have I'll take this current right here. So I'm going to have a current that's flowing, and I'm going to take a surface. So I'm going to take this as just as I used to draw my Gaussian surfaces with a dotted line. Now I'm going to draw this Amperes path with a dotted line. I don't really hear it referred to as Amperes path, but it should be. If they're called Gaussian surfaces, it should be called Amperes paths. And this is a two-dimensional. It's really hard to represent this, but it's two-dimensional. So we have this two-dimensional. Think of it as like a dinner plate. A dinner plate, and the current is passing through the middle of the dinner plate. So that's like the point at which it penetrates through the dinner plate. So I know that this is going to, and I'm putting my thumb in the direction of the current, so it is as behind, it's going to be pointing to the left, Over here it's going to be pointing down. Now I'm in front, and it's kind of difficult to represent that, but in front it's pointing to the right, and then to the right it's pointing up. So I do know the direction in which it's rotating because I can use my right hand to get that. But what is the magnitude of that? And the answer is that it can be found from Amperes Law. We know that that because we've chosen the symmetry of this circle to match the symmetry of the problem, we know that b is going to be a constant. And because b is a constant, we can move it outside of the integral. And then the integral of just dl is basically going to just become b, and in this case I'm going to refer to it as b sub phi. I can do better than that with my phi. B sub phi multiplied by the length of the path. I can do better than that with my length of the path as well. So here's the length of the path is equal to mu sub 0 times the enclosed current. And the enclosed current is however much current passes through passes through the surface that's defined by that two-dimensional path. So actually, I've basically, I guess I didn't need to write that out because it also appears in equation 11.10. And then because we almost always want to just calculate b, I've got equation 11.11. And that one probably deserved to have a box around it because we're going to be using that equation in all of the examples for the rest of today's lesson. There is also a point form to Amperes Law, and so here's the point form of Amperes Law, and this is why we had to learn the curl, is because Amperes Law in point form requires a curl, and the curl of B is equal to mu sub 0 times the current density. So notice that whereas up here in the integral form, we were considering more of a macroscopic level where we're looking at sort of the entire vicinity surrounding a current. Down here we're looking at the microscopic level where it's just, I've got this tiny little amount of current density J, and I want to know how much B is surrounding that J, and that's true at every single point. So equation 11.12, you use the curl of B to find out how much magnetic flux density comes from a current density J. Now both the point form and the integral form involve this constant mu sub 0, and interestingly the units of mu sub 0 are henries per meter. Now the Henry is the unit of inductance. We haven't even seen inductance yet, but we're going to see it very soon. Just be aware of the fact that the units are henries per meter and that the size of the Henry was selected so that mu sub 0 would be a nice round number. So it's not a coincidence that this is 3 lines. That means that it is defined as. So mu sub 0 is defined as 4 pi times 10 to the minus 7th henries per meter. That is the exactly correct value. So whereas before when I said epsilon 0 is 8.854 times 10 to the minus 12th, that was true to 4 significant figures. This is true to infinite significant figures. But here is, because plugging 4 pi times 10 to the minus 7th into your calculator all the time is a real hassle, here is the value of mu sub 0 to 5 significant figures. So we can get it pretty much as precise as we need it to be. Okay, I've only got, an inch and a half at the bottom of the page here to do this example, but it doesn't take very much. I've got a magnetic flux density, so I want to find the magnetic flux density surrounding a line of current I. Assume that the current is flowing into the page. Okay, it's time, if you haven't encountered this yet, for the notation that a circle with an X through it is flowing into the page, and a circle with a dot in it is flowing out. And so here is circle with an X is flowing in. So somewhere, either in your memory banks or somewhere on a piece of paper, you want to write that. And then I'm going to have, and so this is a current that is flowing into the page, and I'm going to take a path around this current. I got my Amperes path here, and the distance is rho. Okay, so I have my fundamental equation, B times L is equal to mu sub 0 times I enclosed. And usually there are 2 things that we need to figure out. What is L and what is I enclosed? Well, I enclosed here is pretty easy. I enclosed is just I. We were told that the line of current is I. And so therefore the entire piece of current is flowing through our path. And so therefore I enclosed is equal to I. L is going to be equal to 2 pi times rho. That's the circumference of a circle that has a radius of rho. So I can say B times 2 pi rho is equal to mu sub 0 times I, or B is equal to mu sub 0 times I over 2 pi rho. And there we go. Now, it's always good to do a reality check here. I would expect that stronger currents would yield stronger magnetic flux densities, and sure enough, the I is in the numerator, so I'm feeling pretty good about the fact that as I increases, the magnetic flux density would increase. I would also think that the further away I get from this current, the magnetic flux density would decrease, and good thing rho is in the denominator, so as rho increases, the magnetic flux density will also decrease. So I'm feeling pretty good about that. Now, you might remember that in Gauss's law, I said, oh, you should be happy if you have hollow surfaces, and solid surfaces are a bit harder. Well, here's an example that is a solid surface. So determine the magnetic flux density for all values of rho for a cylindrical conductor with uniform current density and a total current of I. We're going to do the hardest case first. We're going to consider when rho is less than A. Now, if rho is less than A, then I'm inside the conductor. And I know that I'm not going to capture the entire value of I. I'm going to capture a portion of it, but I'm not going to capture all of it. Now, it does say that it has uniform current density. So that means that it's easy for us to calculate J. J is equal to the total current divided by the total surface area. And the total surface area is simply pi a squared. So this is I divided by pi a squared. I also know that I enclosed can be calculated as a surface integral. Don't worry, we're not actually going to need to do a surface integral. I just wanted to remind you that this is where it all comes from. And in reality, this is equal to J times whatever the area that is enclosed within this surface is. So this area here is A enclosed, whereas the overall area is the total area A. So the area that is enclosed, is equal to pi rho squared, and the total area, as we saw, was pi a squared. So J was I divided by pi a squared. The area enclosed is pi rho squared. The pi's are going to cancel, and I'm left with I times rho squared over a squared. Let's just check if rho equals A, then that term in parentheses is equal to 1, and we've captured the entire amount of current. So I'm feeling pretty good about that. If rho goes to 0, then we've got no surface area, and we've also got no current. So I'm feeling pretty confident there. Now, I know that I'm going to have, let's see, the current is coming out of the page. So when and you can't see me poke my thumb in the direction of the current, but I just did. And so therefore, I'm going to be able to figure out that I've got B sub phi flowing in that direction. And what is the value of B sub phi? Well, B sub phi is mu sub 0 times I enclosed divided by L. And this is mu sub 0 times I rho squared over a squared. And what is the length of that path? The length of that path is 2 pi rho. And we're talking about the length of the path that is the Amperes path shown right here. Well, this row cancels with one of those rows. I'm left with mu sub 0 I times 1 rho divided by 2 pi a squared. Yes, that is correct. And if we're outside, this one's much easier. I did the hard part first. If we're outside of the conductor, then I enclosed is just all of the I. We get all of the current. And the length of the path is still 2 pi rho. And so B sub phi in that case, mu sub 0 I enclosed divided by L is equal to mu sub 0 times I divided by 2 pi rho, and that is it. Let's consider the case where rho is equal to A. So if we're right at the surface, well, if up here, if this one we have, if rho is equal to A, then we end up with B sub phi is equal to mu sub 0 I over 2 pi, and the rho, which is now an A, will cancel with one of the A's from the denominator, and we're left with mu sub 0 I over 2 pi A. And it's pretty obvious that if we had rho equals A, we'd also get mu sub 0 I over 2 pi A right here. So although it wasn't asked in the problem, I think this is really cool. So this is rho, and this is B sub phi. Let's pick a point here and call it A. And this is going to be mu sub 0 I over 2 pi A. And we know that up here, it's a linear relationship increasing with rho. So it's going to go up linearly. Sorry, that almost hit that point. And then down here, it's going to be 1 over rho. And so it's going to drop off as 1 over rho there. Eventually, when you get infinitely far away from this, that's going to go to 0. But it's very important that we see, just as the electric field had to be continuous, in the same way, magnetic field must also be continuous. Just wrapping things up today, I wanted to talk to you about solenoids. Just want to take a minute and I really admire this picture. This was it's actually a simulation. It's not an artist's rendition. It's a simulation, and I would encourage you to visit this gentleman's website. He's got a lot of really amazing pictures there. This is a solenoid. A solenoid is simply a coil of wire, and that coil of wire has a current that passes through it. And so in this case, we've got a current. Let's imagine that the current is flowing downward on the front of each of these lines. And if you put your thumb in the direction of that downward path, you could see that inside the coil here, each one of these is going to create a magnetic flux density. I know it's hard to see this because it's on top of the picture, but that magnetic flux density is going to flow in this direction. Now, magnetic field lines don't have a start or a finish, so therefore they have to wrap around back to here. And maybe they would wrap around like this. And you can see actually the purple lines that are shown outside of this page. Oh, those crossed. They shouldn't have crossed. So as this is doing this, and then this is doing this, and this is doing this, and in this case we would see that this is the North Pole and this is the South Pole, and this solenoid is really just an electromagnet. That if we coil a wire together, we get an electromagnet that we can use to create a magnetic field that we can turn on and that we can turn off. The question is, how strong is that magnetic field? So let's consider the flux density inside a solenoid with n turns of wire, a radius of a, which won't really be important, a length of d, which isn't really important, and the current I that's flowing through it. D is actually going to be pretty important. And then you can assume that the length d is much greater than the radius a. And really what that gets us, if the length d is much, much greater than the radius of a, that means that we can assume that all the magnetic field is constant inside the solenoid. So we're going to assume that we can take the magnetic field at any point inside the solenoid. Now I want you to imagine that we're going to take one of these solenoids, we're going to chop it down the middle vertically. So we're going to have a whole bunch of wires, and I'm not going to draw 50 wires, but we have several wires, and then they have to come in pairs. And sorry, that's not a very good artist rendition. These, I'm going to have the current going into the page. And for these, I'm going to have the current coming out of the page. You know what? That's not good. I need to do this. I need to do that better. Okay. So we have currents going into the page and currents coming out of the page. And what I'm going to do now is I'm going to choose a very particular path for my Amperes Law. And that's the path that I've chosen. Now, I can assume that the magnetic field down here, actually I'll say that the magnetic field times the length is approximately equal to 0 on the two ends. So whether you say I'm taking a very narrow, a very short rectangle, or whether you say, well, the magnetic field is actually kind of perpendicular to those points as it's flowing out, it's perpendicular to those points, so maybe we don't need to consider it, but we're going to ignore the two ends. We're going to say that inside here, and I'm just going to take a minute and consider, yes, it's pointing this direction because of the way that I've drawn the currents. I just did the right hand grip rule there to figure that out. So, yep, coming out, yes, pointing to the left. And in order to close the loop, I know that it's going to be pointing in this direction down here. And let me just remind you, if I scroll back up to that picture, that although it's kind of hard to see, you can notice that each one of these lines, and I realize now that I've drawn the North Pole and South Pole opposite of this figure in the analysis below, but just realize that the magnetic field lines have to continuously loop back. They have to close the loop. And so that's why we have to say that the magnetic flux lines outside are equal to the magnetic flux lines inside. So let's consider now this path is just going to consider the bottom half. Notice that we aren't really considering the top half at all. Up here, this would be the top half. We aren't considering those yet. So we're going to just consider the bottom half. Well, we know that B times L is equal to mu sub 0 times I enclosed. And L, in this case, we have a D inside on the top and we have a D outside on the bottom. So this is equal to 2 times D. And the I enclosed is equal to, there are N coils, so if we have N times I amount of current is puncturing through this surface. So we have B times 2D is equal to mu sub 0 times Ni, and therefore B is equal to mu sub 0 Ni over 2D. That's for the bottom half. We get the exact same result for the top half. And as a matter of fact, you can again use the right-hand grip rule to prove that both the top half and the bottom half are both pushing the current going to the left. And again, I just want to emphasize now, the way that I've drawn this by accident, the north pole is on the left, south pole is on the right. So the total B is equal to mu sub 0 Ni over 2D plus mu sub 0 Ni over 2D, where this is from the top and this is from the bottom. And when we add those two together, we get mu sub 0 Ni over D. And that is our final answer for the strength of the magnetic flux density inside this solenoid. So notice that as you add coils, as you add N, you're going to get a higher and higher magnetic flux density. But as you make the coil, as you make the solenoid longer, you're going to get a lower magnetic flux density. So your ideal would be a whole bunch of coils that don't take very much, they don't spread out very much horizontally. You'd like them to all be right on top of each other. But of course, even with very thin wire, they can't all be directly on top of each other. So in practice, it will have to kind of do this a little bit, but you do want to minimize that if all possible. So you'll tend to end up with multiple layers of these coils so that it becomes as short as it can possibly be. Last thing for today, we can wrap the solenoid so that it bends back onto itself, makes kind of a donut. And that's known as a torus. You know, next time you're eating a donut, you think, oh yeah, this is a pretty good torus. Or a toroid, that's when we have a solenoid that's bent in the shape of a toroid, we often refer to it as a toroidal solenoid. So if you really want to impress your friends, you can just say, oh, I studied toroidal solenoids today. So let's consider what happens with this toroidal solenoid and how strong is the magnetic flux density there. Good news for you, we've only got, again, a couple of inches, so this can't be very hard. So we're going to have a top view now. So I've got a top view of this toroidal solenoid, and I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. I'm going to have it going into the page inside, and I'm going to have it coming out of the page on the outside. And then I'm going to take my Amperes path here, and that's supposed to be a circle. Sorry about that. Okay, and so then I know that if I put my thumb in the direction of current flow, right-hand grip rule, it's going to be flowing in that direction. And if any of these, if you can't figure out how these directions are working out, ask me. Come and talk to me, or see me before or after class or during class. I'd be happy to talk to you about it. So I know that B is equal to mu sub 0 times I enclosed divided by L. Well, L here, we know that this has a circumference of D, so L is equal to D. And we know that there are N coils, so I enclosed is equal to N times I. So B is equal to mu sub 0 times N times I over D. Turns out that a solenoid and a toroidal solenoid both give exactly the same calculation of the magnetic flux density inside of them. Sometimes you'll have an application for one that's better. In other cases, you'll have an application for another. Typically, just a regular straight solenoid would have lots of industrial applications, lots of places where you need an electromagnet to do something, and a solenoid will do it for you. So today we studied the curl. We saw that the curl can be calculated according to a determinant. I've only shown the rectangular form here, but there's also cylindrical and spherical. We saw that magnetic fields are caused by moving charges. The strength and direction of the magnetic field is represented by the magnetic flux density B, which has units of Tesla. We saw that magnetic flux lines do not have beginnings and endings. They always create complete loops. So therefore they have no sources and no sinks. And this then becomes, there are no magnetic monopoles, which is the second of Maxwell's equations. We have both an integral form and a point form, as we do with all of Maxwell's equations. Permanent magnets are created when ferromagnetic material, iron, nickel, cobalt, is subjected to a strong external magnetic field, possibly with heat, possibly with physical, vibration as well. And hysteresis then will cause, the domains will tend to rotate and align in the same direction as the externally applied magnetic field. Hysteresis will then cause that to remain, or substantially remain, even after the magnetic field has been removed. And only ferromagnetic materials will do that. Amperes Law can be used to determine the strength of magnetic flux density surrounding a current element, and the right-hand grip rule can be used to determine the direction. So we have the formal, official version of Amperes Law in its integral form, but then, because we're almost always going to choose the symmetry of the problem correctly, we'll end up with the simpler version, and then of course we have the value of mu sub 0 there. The magnetic flux density surrounding the line of current has this form right here, and the magnetic flux density inside a solenoid or inside a toroidal solenoid has this form here.